Category O, Lecture 2, Highest Weight Modules. Let's start with some notation and setup. For Lie algebra A, we denote by U of A the universal enveloping algebra of A, and by Z of A the center of U of A. G denotes a semi-simple finite-dimensional complex Lie algebra, and H is a fixed Cartan subalgebra of G. We recall that H is abelian. We have the root space decomposition of G into a direct sum of H together with a direct sum of all root subspaces G alpha, where alpha runs through the root system phi of G. The root system phi is a subset of the dual space of the Cartan, and we fix a decomposition of phi into a disjoint union of positive and negative roots. This means that we fix a basis pi of phi. Then positive roots are exactly the roots which can be written as linear combination of basis elements with non-negative integer coefficients, and negative roots are the negations of the positive roots. So this gives us a triangular decomposition of G, which means a decomposition of G into a direct sum of three subalgebras, and minus, which is a direct sum of all root subspaces corresponding to negative roots, H, which is our Cartan subalgebra, and n plus, which is the direct sum of all root subspaces corresponding to all positive roots. So we denote by W the Weil group of our root system phi. Let's start with a brief discussion of weight modules. For an element lambda in the dual space of the Cartan subalgebra, and for any G module M, denote by M lambda the set of all elements M in M, having the property that each element H from our Cartan subalgebra H acts on M via the scalar lambda of H. The usual terminology is that elements lambda in H star are called weights. This space M lambda is called the weight space corresponding to the weight lambda, and any element V in M lambda is called a weight vector of weight lambda. A module M is called a weight module, provided that it can be written as a direct sum of its weight spaces. And if we have a weight module M, then the support of M is defined as a set of all weights for which the corresponding weight spaces are non-zero. We define WGH as the full subcategory of the category of finitely generated G modules consisting of all weight modules. So we want to get some decomposition of WGH into smaller subcategories. The principal observation to obtain this decomposition is the following. If we have any root alpha, any weight lambda, and any G module M, then the root space G alpha sends all elements of the weight space M lambda to the weight space M lambda plus alpha. To prove this, take any element V in M lambda, any element G in G alpha, and any element H in H. So we want to find out what is the eigenvalue with which H acts on the element GV. To do this, we commute H past G. The price to pay for this is that we have to add the commutator of the elements H in G. When we commute H, then we have G applied to HV, and since V was an element in M lambda, H times V is equal to lambda H times V. So altogether we will get lambda H times GV. Since G was an element in G alpha, the commutator of H and G is alpha of H times G. Now if we collect this together, we get the element GV times the scalar given by lambda plus alpha evaluated at h. This means exactly that GV is an element in M lambda plus alpha. So this observation motivates the following. For any coset psi of the dual space of the Cartan, modulo the additive subgroup generated by all roots, let us denote by WGH psi the full subcategory of the category of weight modules, which consists of all modules M whose support belongs to psi. So the point for this notation is the following. If we have a weight module M, which is generated by the weight space M lambda, and if we apply to this weight space all elements of the universal enveloping algebra, the outcome is just obtained from M lambda by applying inductively different root spaces G alpha. Applying G alpha to M lambda, we shift lambda by alpha. If we do it several times, we can shift lambda by an integral linear combination of all roots, which means that the support of such module will belong to the coset of H star modulo the integral additive subgroup generated by all roots. So this is his justification for this notation. So if we take into account that if we have two modules M and N, and any homomorphism from M to N, then the homomorphism commutes with the action of the Cartan subalgebra and hence sends each weight space M lambda to the corresponding weight space N lambda. Taking this into account, we have the following corollary. The category WGH decomposes as a direct sum of subcategories WGH psi, where psi runs through the set of all cosets of H star modulo the additive subgroup generated by all roots. So in particular, this observation says that there are no homomorphisms between modules in different subcategories, and the principal observation says that if we start from one particular weight space, then the G module generated by that weight space will belong to one of these direct summands. This implies existence of such a decomposition. So some weight terminology. A weight module is called a module with finite dimensional weight spaces, also known as a Harish-Chandra module, provided that all weight spaces of this module are finite dimensional. A module is called uniformly bounded if the dimensions of all weight spaces of this module are uniformly bounded. A weight module is called pointed if all weight spaces of this module are at most one-dimensional. And the weight module is called dense, provided that the support of this module is maximal possible, that is, coincides with some coset of H star modulo the additive subgroup generated by all roots. So let's consider the following SL2 example. So SL2 is a Lie algebra with a standard basis consisting of F, H, and E. H is a Cartan element, F is a lower triangular matrix, and E is an upper triangular matrix. Let us fix two complex numbers, lambda and C, and define the SL2 module V lambda C in the following way. So we have a basis of this module which is indexed by elements in the coset of lambda plus 2z. The Lie algebra SL2 has two roots, 2 and minus 2. So this is exactly lambda plus the additive subgroup of H star generated by the roots. And in this basis, define the action of our elements of SL2 in the following way. Each basis element v mu is an eigenvector for H with eigenvalue mu. F shifts all v mu to v mu minus 2, so it shifts everything to the smaller value of mu. And E shifts each v mu to v mu plus 2 times some scalar. And the scalar c mu is given by the following expression. It's 1 over 4 times c minus mu plus 1 squared. Pictorially, we can draw the module v lambda c as the following picture. So we have the basis elements v mu minus 2, v mu plus 2. So we have infinitely many basis elements. The element h acts on v mu with a scalar mu. So we have these loops in our graph which represent the action of h. The action of f is given in the following way. So it moves all basis vectors to the left, v mu to v mu minus 2. And the action of E moves all basis vectors to the right times the scalar c mu. Claim: this v lambda c is an SL2 module. So for SL2, we need to check three defining relations. The fact that the bracket of H and E is equal to 2E is equivalent in this module to the fact that E maps each v mu to a linear span of v mu plus 2. The defining relation that the commutator of H and F is equal to minus 2F is equivalent to the statement that F sends each v mu to a linear scalar of v mu minus 2. And finally, the relation that the commutator of E and F is equal to H is equivalent to the relation that the difference between c mu minus 2 and c mu is equal to mu. So the commutator of E and F is a difference of this loop, and this should be equal to mu. And it is easy to compute that c mu are designed so that this relation holds. Therefore, v lambda c is indeed an SL2 module. We claim that this module is simple if and only if the value of c is not equal to mu plus 1 squared for any mu in our coset lambda plus 2z. Indeed, our module by definition has a basis which consists of eigenvectors for h with different eigenvalues. Therefore, any submodule of our module must contain some of these basis vectors. So starting from this basis vector v mu, applying the element f, we can get all vectors to the left, and f acts always in a non-zero way. Applying the element e, we can go to the right under the assumption that all coefficients c mu are non-zero. So if all coefficients c mu are non-zero, which is equivalent to our assumption, then applying f and e, starting from v nu, we can obtain all our basis vectors, which means that our module is simple. If some c mu is 0, then the linear span of all basis vectors to the left of v mu is clearly a submodule. We cannot go to the right from v mu. Therefore, in this case, the module v lambda c will not be simple, which completes the proof of our claim. So by definition, we see that the module v lambda c is dense and pointed. And there is a general theorem that any simple SL2 module, which is a weight module, is in fact a subquotient of some v lambda c. For the proof, I refer to the chapter 3 of my SL2 book. So here are some general properties of weight modules. Submodules of weight modules are weight modules. So if you have a module on which H acts semi-simply, it should act semi-simply on any submodule. Quotients of weight modules are weight modules. Again, if H acts semi-simple on some space, it acts semi-simply on any quotient. Direct sums of weight modules are weight modules. This is clear. A module generated by a weight vector is a weight module, or a module generated by a set of weight vector is a weight module. So this follows directly from this principal observation. If we start from a weight space and apply root elements, we get weight elements. So if we start from a weight space and apply U of G, we end up in a direct sum of weight spaces. So this means that a module generated by a weight vector is a weight module. All finite dimensional G modules are weight modules. For simple finite dimensional G modules, this is the previous claim. If you have a simple finite dimensional G module, it obviously has a weight vector because it has a simple submodule for H. And the claims that all finite dimensional modules, not necessarily simple finite dimensional modules, are weight modules, is an equivalent to Weil's complete reducibility theorem that all finite dimensional G modules are semi-simple, that is, direct sums of simple finite dimensional modules. And as we just discussed, any simple finite dimensional module is a weight module. A couple of warnings. An extension of weight modules is not a weight module in general, because if you extend to modules where H acts semi-simply, then on the extension, H can in principle act using Jordan cells of size at most 2. The regular module U of G is not a weight module. The action of H on U of G is free. It's the opposite of being semi-simple. And also, there exist weight modules with infinite dimensional weight spaces. The smallest algebra for which such modules exist is SL3. In general, such modules exist for all semi-simple algebras which are not direct sums of copies of SL2. Let's now go to highest weight modules. So the notion of a highest weight is a notion with respect to some partial order on the set of the weights. For two weights, lambda and mu, we say that lambda is less than or equal to mu if the difference mu minus lambda can be written as a linear combination of positive roots with non-negative integer coefficients. This relation is a partial order on H star, which follows from the fact that the basis of our root system consists of linearly independent vectors. And now the main definition. For a weight module M, a weight lambda in the support of M, which is maximal with respect to our partial order less than or equal to, is called a highest weight of M. As a small remark, each finite dimensional module obviously has a highest weight. So it has finitely many weights, so one of these weights is a maximal element, of course, because we have a partial order. So for example, if you consider the Lie algebra SL2, so for each n, there is a unique n plus 1 dimensional simple SL2 module, and this module has weights n, n minus 2, n minus 4, and so on. The algebra SL2 has a unique positive root, which is 2. So out of these elements, the only weight such that n plus 2 is not a root is the weight n. So the weight n is the unique highest weight of this module. So the simple n plus 1 dimensional SL2 module has highest weight n. A negative example. Dense module, by definition, do not have highest weights. Their support coincides with the coset with respect to the integral span of all roots. Therefore, for any element lambda in the support of a weight module and for any positive root, lambda plus alpha is again a root. So dense modules do not have highest weights. So now the next main definition, a G module is called the highest weight module if it is a weight module and it is generated by a non-zero highest weight vector. So a non-zero vector belonging to some highest weight space. So example, simple finite dimensional modules are obviously highest weight modules because they have highest weights and they are generated by any non-zero vector. And the main aim of this talk is to provide a classification of all simple highest weight modules. We will construct simple highest weight modules using Verma modules. So before we define the Verma modules, we make the following observation. Then if lambda is the highest weight of a weight module M, then the positive part of the triangular decomposition, the Lie algebra N+, kills the weight space M lambda. Indeed, if alpha is a positive root, then the corresponding root space G alpha maps M lambda to M lambda plus alpha. We had this observation before. However, lambda plus alpha is greater than lambda. Therefore, lambda plus alpha cannot be in the support of M because lambda is assumed to be a highest weight. This means that M lambda plus alpha is 0, which proves our observation. So now, for a weight lambda, consider the corresponding one-dimensional H module C lambda, on which elements of our Cartan subalgebra act via scalars prescribed by lambda. So now we can take N plus and postulate that N plus kills our C lambda. In this way, we define on C lambda the structure of the module over the Borel subalgebra H plus N plus. So Verma modules were defined by Verma in his PhD thesis in 1966. So the Verma module delta lambda associated with lambda in H star is defined as the module, as the G module obtained from the B module C lambda by tensor induction. So delta lambda is equal to U of G tensor over U of the Borel subalgebra applied to the module C lambda. So this is a Verma module corresponding to the weight lambda. Let's do the SL2 example. So fix a weight lambda, so in SL2 case, lambda just a complex number, and denote by V the basis element of the one-dimensional complex module C lambda. So we have that our basis element H acts on V using the scalar lambda, and E kills the element V. E is the element of our N+. Using the PBW theorem, using the Poincaré-Birkhoff-Witt theorem, we know that the linear span of standard monomials of the form f to the power I, h to the power j, e to the power k is a basis of the universal enveloping algebra. So since the elements of the Borel subalgebra h and e can be moved over the tensor product during the induction process, it follows that the Verma module delta lambda has a basis consisting of the vectors f to the power I, tensor v. V is our generator, and here I is a non-negative integers. Pictorially, we can draw our module, our Verma module delta lambda in the following way. So we have the canonical generator 1 tensor v. Applying f, we get f tensor v, f square tensor v, and so on. So 1 tensor v is a weight vector for h with weight lambda. F tensor v is a weight vector for h with weight lambda minus 2, and so on. And f moves everything to the left with coefficient 1. E maps everything to the right, and we need to compute what kind of coefficients we will get. A very easy computation shows that E maps f tensor v to lambda times 1 tensor v. It maps f squared tensor v to 2 times lambda minus 1 times f tensor v, and so on. And from this picture, if we take into account how we computed the simplicity of the SL2 modules V lambda C, we deduce that the Verma module delta lambda is simple if and only if lambda, the parameter lambda, is not a non-negative integer. Indeed, under this condition, all coefficients of the action of E are non-zero, of course apart from the action of E on the highest weight vector 1 tensor lambda. So we can use exactly the same argument as for V lambda C to prove that this module is simple. And if lambda is a non-negative integer, then one of these actions of V will be 0, and therefore everything to the left of that 0 will be a proper submodule. So here are some elementary properties of Verma modules. Verma modules are weight modules. Of course, they are generated by a weight vector. They are also highest weight modules with highest weight lambda. As a vector space, Verma modules are isomorphic to the universal enveloping algebra of the negative part. In fact, they are also the Verma modules are isomorphic to this universal enveloping algebra as modules over this universal enveloping algebra. And this follows directly from the Poincaré-Bergoff-Witt theorem. So we can move elements from the positive part and from the Cartan over the tensor product. So here, this is a definition. The elements from n plus can be moved over. Elements from H can be moved over. What is left here is un minus. So delta lambda as a vector space is isomorphic to un minus. And because of that, and because the highest weight of delta lambda is the weight lambda, the support of lambda consists of all vectors, which can be obtained from lambda by subtracting positive roots, alternatively by adding negative roots. Moreover, we can see that the dimension of the weight space mu in the module delta lambda equals the number of ways you can write the difference of lambda minus mu as a linear combination of positive roots with non-negative integral coefficients. This is what is known as Coston's partition function. In particular, it follows that this dimension is finite. So each Verma module is a weight module with finite dimensional weight spaces. So by definition, delta lambda is generated by the weight space delta lambda lambda, and the dimension of this weight space is 1, so it corresponds to constants in the universal enveloping algebra of n minus. Any root subspace of n minus shifts lambda to lambda minus alpha, where minus alpha is a corresponding negative root. And delta lambda is a highest weight module with unique highest weight lambda. So all other elements in the support of delta lambda are clearly smaller than lambda. Okay, let's consider examples and what are the supports and multiplicities of Verma modules. So for the Lie algebra SL2, we have two roots, alpha and minus alpha. Alpha is equal to 2, so this is the value of the root alpha at our element H. And the support of our module delta lambda, we start with lambda and we subtract negative roots. So we get lambda minus 2, lambda minus 4, lambda minus 6, and so on. And all weight multiplicities will be 1. Because if we want to go from lambda to, say, lambda minus 6, the only thing which we can do, so we can write the difference 6 as a linear combination of positive root 2. Only in one way, it's 3 times 2. So all weight spaces of the Verma module for SL2 will be 1. It will be more complicated for SL3. So here is a root system for SL3. We have 6 roots, 3 positive roots, alpha, beta, and alpha plus beta, and 3 negative roots, minus alpha, minus beta, and minus alpha minus beta. So the support of the Verma module M lambda then looks as follows. We start from lambda, and we are allowed to go along negative roots. So lambda minus alpha, lambda minus 2 alpha, and so on. Lambda minus beta, lambda minus alpha minus beta, lambda minus 2 alpha minus beta, and so on. Lambda minus 2 beta, lambda minus alpha minus 2 beta, and so on. So if we look at weight multiplicities, then there is only one way how we can write alpha as a linear combination of positive roots. So the weight multiplicity of lambda minus alpha is 1. The weight multiplicity of lambda is 1 always. Similarly, there is only one way how we can go from lambda to lambda minus 2 alpha. We subtract alpha twice. So along the edge here, so along the boundary of our support, we will always have weight multiplicities 1. However, if we go to lambda minus alpha minus beta, so alpha plus beta can be written as a linear combination of positive roots in 2 different ways. First of all, as alpha plus beta, and second, as alpha plus beta. So the weight multiplicity of this subspace in the Verma module is 2. And similarly, one sees that the second line along the edge has all weight multiplicities equal to 2. Then the third line will have all weight multiplicities equal to 3, because 2 alpha plus beta is either 2 times alpha plus beta, or alpha plus beta plus alpha plus beta, or 2 times alpha plus 2 times beta. So we will have multiplicity 3 here, multiplicity 4 next, and so on. In particular, we see that Verma modules over SL3 are not bounded. There is no uniform bound on the dimension of the weight spaces, but all weight spaces are finite dimensional. Next, let us talk about the universal property of Verma modules. For a G module M and the weight lambda, denote by k lambda of M the set of all weights V in M which are killed by n plus and on which elements of the Cartan subalgebra act as scalars prescribed by lambda. The universal property of Verma modules is the following statement. For any G module M and any weight lambda, the vector space of all G homomorphism from the Verma module delta lambda to M is isomorphic as a space to the space k lambda of M. So this is proved using the usual induction restriction adjunction. The space of all homomorphism from our Verma module to M can be computed using the fact that the Verma module is induced from a module over the Borel subalgebra. By adjunction, this home space is equal to the home space over the Borel subalgebra from C lambda to M. And the later home space is isomorphic to k lambda of M by sending the canonical generator of C lambda to an element V in k lambda of M. So C lambda is a module over the Borel which is killed by n plus and where H acts via scalars prescribed by lambda. And this is exactly the definition of k lambda of M. So this proves a universal property. Corollary from this universal property is that any simple highest weight module with highest weight lambda is actually a quotient of the Verma module delta of lambda. Indeed, if L is a simple highest weight module with highest weight lambda, then the weight space L lambda should be non-zero. But since it's a highest weight space, then the corresponding space k lambda of L should coincide with it, because being a highest weight it is killed by n plus. By the universal property, this implies that there is a non-zero homomorphism from delta lambda to our module L, and since L was supposed to be a simple module, any such homomorphism is surjective. This means that any simple highest weight module with highest weight lambda is a quotient of delta lambda. So the next natural question is, how many different simple quotients can a Verma module delta lambda have? And the answer is only one. So the claim is that delta lambda has a unique maximal submodule. Recall that the weight space of weight lambda in delta lambda is one-dimensional and generates delta lambda. Therefore, any proper submodule n of delta lambda cannot have anything in weight lambda, because anything non-zero generates the whole module. So any proper submodule should miss the weight lambda. But then if you take the sum of all proper submodules, the property that the sum misses the weight lambda is still preserved. So this sum is the unique maximal submodule of delta lambda. And if we factor out this unique maximal submodule, we obtain the unique simple quotient of delta lambda, which we denote by L lambda. Recall that delta lambda had a unique highest weight lambda, so L lambda also has a unique highest weight, namely lambda, which implies that L lambda and L mu are isomorphic if and only if lambda is equal to mu. A corollary from that the set of modules L lambda, where lambda is an element from the dual space to the Cartan subalgebra, this set is a complete and irredundant list of representatives of isomorphism classes of simple highest weight modules. On the previous slide, we saw that each simple highest weight module with highest weight lambda should be a quotient of delta lambda, and here we see that such quotient is unique. So the list of all L lambdas is exactly the list of all simple highest weight modules. Let's do the SL2 example. So we have seen the Verma module delta lambda, which had the following picture, and we discussed that this module is simple if and only if lambda is not a non-negative integer. So if lambda is not a non-negative integer, then delta lambda coincides with L lambda. So if lambda is a non-negative integer n, then delta n has a unique simple quotient, which is the n plus 1 dimensional simple SL2 module Vn. So if lambda is equal to n, then the coefficient of the action of E on the element f to the power n plus 1 tensor V will be n plus 1 times lambda minus n, which is 0 if lambda is equal to n. So everything to the left of this vector is a submodule. When we factor it out, what we get is exactly the n plus 1 dimensional simple module Vn. Therefore, simple highest weight modules for SL2 are the Verma modules whose highest weights are not non-negative integers, and the simple finite dimensional modules, which are classified by non-negative integers. So in the general case outside SL2, there are many simple highest weight Verma modules, and of course all simple finite dimensional modules are simple highest weight modules, but there are also many things in between. And this is an interesting part of our story. So we complete the lecture with some problems for PhD students. So let L be a simple module over the Borel subalgebra. Can one claim that the module L is isomorphic to C lambda for some lambda? What about the same claim if we assume that L is finite dimensional? So question 2. Is the home functor from a Verma module exact on the category of all G modules? What about the category of all weight G modules? Question 3. This is a very important property. Prove that Verma modules have trivial endomorphism rings. Any endomorphism of a Verma module is a scalar. Question number 4. Prove that any non-zero homomorphism from the simple highest weight module L lambda to the Verma module delta lambda is an isomorphism. Finally, question number 5. Determine all eigenvalues of all positive root elements on all Verma modules. Thank you very much. See you next time.